be 1, and the model would then predict completely insane, bizarre behavior that we never observed. So we like to keep it strictly between 0 and 1. So what that means is that the discounted utility of a plan just becomes this very simple sum. Right? It's delta to the t times the utility that you expect to get from consumption at time t added up over all t's. And what that winds up looking like is, so delta to the 0 is 1. Right? So in the first period, there's no discounting. So you just get u of x naught plus delta u of x1 plus delta squared u of x2, etc. Either up to infinity or up to capital T. So if you look at this, sum, it's basically a weighted sum, just like expected utility, right? Yeah, David. Well, so if there's interest, for example, you just never consume anything. You just always save everything because you'd be a gajillionaire in the infinite future. We don't see that. That doesn't make any sense. So that's the kind of thing. It has a lot. It's especially problematic when you have infinite sequences. Here's another example. If I can make an investment, a capital investment now, that pays off with a small benefit in each period in the future, if I want to model that as an infinite stream because it's going to go on forever, maybe my heirs will benefit from that. If I don't discount the future at all, I should be willing to make any arbitrarily costly investment now because I'm not discounting the far, far distant future stream of benefits from it. So you get hokey stuff like that. Okay, so this is a weighted sum. We like weighted sums, right? Weighted sums are mathematically simple. They're linear. We can do all kinds of simple and nice things with weighted sums. Where we run into problems here relative to where this becomes way murkier is what these weights are. So in the expected utility model, if I got a 50% chance of this outcome and a 50% chance of that outcome, I might not necessarily weight those things exactly equally, but it's a pretty safe bet that how I weight them is going to be pretty closely tied to how likely they are. So using the probabilities as weights is psychologically a lot more compelling than anything that we can come up with in terms of where these deltas or where these discount factors are coming from. Because there's no objective thing. There's nothing like a probability that's objectively there to be observed for us to harness. There's just how far out in the future it is, which is it's just murkier. It's a lot murkier. How far something out in the future how far in the future something happens is just a lot less solid foundation for figuring out what these weights should be than actually having an objective probability to fall back on. Okay, let me give you an example. You can do a lot of really interesting stuff with this model. I'm going to give you one tiny example, and it's a super dumbed down example. So suppose you're making a decision: should I spend $10 now, or should I save it until some future period at an interest rate of R per period? Okay. So here's my two plans, and we're going to ignore all kinds of stuff here. My two plans would be spend it, which plan would look like this. And I'm just going to make this a two-period model, 0 and 1. So the spend plan would be x naught equals 10 and x1 equals 0, and the save plan would be x naught equals 0 and x1 equals what? I hear R. 1 plus R times 10. Okay, and I'm also, by the way, I'm going to make a very simplifying assumption here, which is that your utility function in dollars is just linear. Okay, which means that the person has quasi-linear preferences over everything else. Okay, so those are the two plans, and we're going to choose between these plans. There's no future decisions to be made, so we can say with certainty, if I take this action, I'll get this plan. If I take that action, I'll get that plan. So all I want to know is which plan do I prefer? Okay, so the utility of the spend plan under this instantaneous utility function is just delta to the 0 times 10, which is the utility of the 10 now, plus delta to the 1, because that's in the next period, times the utility I get from future consumption, which would be 0. Okay, so that's just 10. And the utility I get from saving would be delta to the 0 times not having anything to consume now, plus delta to the 1 times the utility I get from having my $10 plus interest in the future. Okay, which is just delta times 1 plus R times 10. We're just going to use the same, we're doing binary utility maximization. In this section of the class, over and over again, we're going to see the same thing, binary utility maximization. I got two choices, which one of them gives me the biggest utility, depends upon whether, so I am going to save if the utility of doing so is greater than the utility of not. Okay, and that decision rule is basically boils down to whether delta is greater than or equal to 1 over 1 plus R. Okay, this is sort of one of the classic insights of the discounted utility model. So basically this says if delta is big enough, you'll save, holding R exogenously constant. So what does it mean if delta is big? All right? You're patient. If delta is big, you're patient. Right? Because delta is how much you discount future utilities. So if delta is close to 1, that basically means you're thoughtfully taking into consideration the fact that you will, in reality, still be you when the future arrives. It's only you're hurting if you ignore the future. In most cases. Well, no, you obviously destroy the environment and wreck the federal budget as well. But at a minimum, you should be looking out for yourself. So if delta is big, it means you care about your future self. One way of thinking about it means you're patient. You're willing to forego current consumption to take care of yourself in the future. Yeah, Andrew. Because we're Paul Samuelson. So Andrew's question was why we assume that delta is the same from one period to the next. It depends on your definition of the word we. We don't. That's exactly where we're going. Yeah. Samuelson made this assumption for exactly one reason, and I'll let you guess what it is. What? Because it's simple. Actually, I'm wrong. It's not the only reason, but it's the same two reasons as we see over and over again. One is mathematical simplicity, and the other is, can anybody guess? It preserves rationality in a very important way. So we're getting there quickly. Well, actually, we're getting there slowly, but we're getting there. Okay, so this is the kind of thing that we can do with this model, and gives you a little insight into what's going on with this discount function. The discounted utility model is a psychological disaster. Now, when I introduced the expected utility model of von Neumann and Morgenstern, I sort of said some rather heartwarming things about it. I said, look, this captures a really important piece of psychological realism, that it makes much more sense that people would evaluate their possible outcomes and then see how they feel about having a mix of those outcomes, of the utilities they get from those outcomes, than to think that they first take an average of a trip to Nepal and a nice retirement and then see how they feel about that average. Because that average is a fundamentally non-existent, meaningless thing. We cannot make any such claims about the psychological realism of this model. It does not involve one shred of forward movement in terms of psychological realism. In fact, it was a huge step backwards. It was more like a huge step sideways. Prior to this model, people have been wrestling for a long time. People like Ray and Böhm-Bawerk, who you'll read about in the assigned reading by Frederick Lowenstein Reed, cogitated in a mostly non-mathematical way about sort of this question that Smith and others had posed the previous century. Why do some people say, why do some nations say and others not? What are the psychological or sociological reasons for this? Maybe there are differences in how much people care about the future well-being of their offspring, so the quest motivation. Maybe there are differences in people's ability to clearly imagine the future, the telescopic facility that you'll read about, or faculty, or people's ability to tolerate self-denial. Okay, so all of these things, you can see psychologists sort of sitting around the samovar drinking endless cups of tea and hashing these things out, but none of them were mathematized. Okay, so Samuelson came along and said, at a period where mathematics was being introduced into economics at a frightful pace, back in the 30s and 40s, and he said, basically, watch this. Watch this clever trick. Okay? And the article, which I need to post, actually, I haven't posted it yet. You should take a look at it. The math is fairly daunting, but the words are really worth reading. It's only about 7 pages long, and it's called A Note on the Measurement of Utility. Right? It's not called A Fantastic New Discovery About How to Model Choices. It's called A Note on the Measurement of Utility, and it is really essentially intended as a note. And basically what he did was he said, look, I'm a mathematician, I do fun math, and look what I can do with fun math. And somehow it turned into the standard model. And you will read a lot more about how that process transpired in Frederick et al. So what happened was, unintentionally, I would argue, Samuelson's discounted utility model took all of that psychological complexity that economists had been trying to wrestle with in a non-mathematic framework and basically just eviscerated it and replaced it with this single parameter delta. Okay? The Samuelson was no dummy. In 1960, Samuelson wrote what became for a couple of decades the standard undergraduate textbook on microeconomics, and he intentionally wrote it without any math at all. Right? So this is a sophisticated thinker. He thought about how to use math carefully and in a sophisticated way, and he himself strongly disavowed the model that he presented in this note. It really was just a conceptual exercise that he was going through. He said, for example, from a positive perspective, it is completely arbitrary to assume that the individual behaves so as to maximize an integral of the form envisaged. So I showed you a summation. He did it in continuous time, so it's an integral. From a normative perspective, a similarly devastating disavowal, the idea that the results of this model, the normative results, could have any influence upon ethical judgments of policy, which is what we mean by normative economics, is one which deserves the impatience of modern economists. Right? I love this kind of language. It has the disadvantage of being so flowery as to be somewhat easy to ignore with a chuckle. But if a famous economist says, this model that I have just written down, if applied to normative valuations, deserves the impatience of modern economists, right? Modern economists don't get impatient that easily. We're very tolerant people. We're tolerant of new ideas. We're tolerant of hokey models. We're tolerant of extreme approximations. We're tolerant of crazy simplifications. And he's saying we should not be tolerant of this model. Okay? Nonetheless, it has been used ever since for positive and normative purposes, to the exclusion of almost everything else that you might want to come up with. From the standpoint of science, this is a tragedy, in my opinion. Okay, so let's look at why that's such a tragedy, or at least begin to get some sense of at least one of the major reasons. There's a lot more about this in the Frederick reading, which is very interesting. So here are a couple things that Frederick et al. Mentioned. Consumption independence, back up. So here's some implications about the instantaneous utility function. So before we even get to the crazy discount factor, there are some assumptions that are embedded in the way the instantaneous utility function is used here. So we have u of x naught plus delta u of x1 plus ... Okay? We're not going to say anything right now about the actual shape of that utility function. That comes back to Pedram's earlier question about would this be a reference-dependent instantaneous utility function. The paper talks about that a little bit, and I'm not going to. But even the way that it's included here in this weighted sum, right? There's no interaction between x naught and utility in any other period. It only enters here. And there's also no interaction between the utility that you get in time 0 and the utility that you get in any of these other periods. Okay, so there's consumption independence and there's utility independence, or separability. So with respect to the consumption independence, what this model is implicitly saying is that the utility you get from consumption in one period, let's say the present, let's say the future, is completely independent of consumption in all other periods, in particular prior periods. Okay, so for example, it implicitly says how I feel about taking drugs today is completely unaffected by whether or not I've taken drugs in the past. Or how I will feel about taking drugs in the future is completely independent of whether or not I get addicted to them now. Right? So this rules out any kind of habit formation, rules out a lot of other things. And that habit formation can be positive too. How I feel about going to the gym today is completely unaffected by whether or not I've been going to the gym in the past, which we also know is not true. We'll talk about that in a couple of weeks when we start talking about state-dependent preferences and projection bias. A second dimension is this utility independence. Okay, so the utility from outcomes in any one period, say the future, has absolutely no impact. So the utility from impacts, let's say in the future, or outcomes in the future, has absolutely no impact on how you feel today. Okay, you take it into consideration when you're choosing what plan you want, because you know that in the future you're going to have to actually experience that utility. But the utility that you're going to get in the future does not affect how you feel today or in between. Okay, so what this rules out is things like worry or fantasy. So if I know I'm going to inherit a fortune next year, it doesn't affect how I feel today. That's one of the things this implicitly assumes. Or if I know that I'm going to be speaking in front of a large audience next week, it doesn't affect how I feel today. And we know that both of those things. Casual introspection tells us that those things are wrong. Okay, so we're going to address this next week when we start talking. We're only going to talk for one lecture about anticipatory utility. Okay, utility that you get now. Right, which is different from taking into account the utility that you'll get in the future. In anticipatory utility models, you will also take into account the fact that if x1 is inheriting a large fortune, that you may like to fantasize about that in period 0. Okay, you shouldn't, because winning that much money usually means that you'll lose all your friends. But anyway, so as I said, that there are other implications, implicit sort of the implicit psychology of this model that have to do with the shape of this utility function, this instantaneous utility function. And there are things like that how people discount the future depends upon the magnitude of outcomes, depends upon whether those outcomes are gains or losses, depends upon whether they involve speeding up outcomes or delaying outcomes. All the kinds of things that you would expect would be affected by loss aversion and diminishing marginal sensitivity. And there's been research on that. It's a bit less compelling than the research on reference dependence under uncertainty because it turns out that the results are just a lot more specific. The assumptions you have to make about the instantaneous utility function are much more specific. Okay, so much for the instantaneous utility function. We'll talk more about the things on that slide. We won't talk about many others. But what we're going to start out with, which is the much more big ticket item really, is the implications of this discounting function. Okay, so the first thing that you want to notice, because this drives everything else, is that if we have a discounting function of this form, this exponential discounting function, and let me just clarify why it's called exponential discounting. If you have a graph where this is 0 and this is 1, so we would expect d of 0 to be 1, right? No discounting in the current period. And then what we get is, here will be, so we have time periods 1, 2, 3, etc., like this. And then we have d of t here and t here. If we're using Samuelson's model, then we would have, say, delta here, and then we would get delta squared, and then we would get delta cubed, etc. And what we'll get is a function that slopes off like this. That is a discrete time version of an exponential function. So it's the discrete time version of, so in continuous time, the way you would model this is that d of t would be equal to e to the negative delta t. Okay? An exponential usually, right, the exponential function does that, right? That's e to the x, and it cuts through at 1. So by putting a negative there, you flip it around so it starts at 1 and goes down, and then that delta just tells you how quickly it goes down. So that's why we call this the exponential discounting model. If you assume that this is that the discount factor is an exponential function of time, what it means is that the discount factor between any two adjacent periods is always the same. It's always delta, right? So I discount period 1 relative to period 0 by delta, and if I extend this, when I look at trade-offs between outcomes in period 2 and period 1, I discount back period 2 relative to period 1 by an additional delta, et cetera, et cetera, et cetera. Okay? So the rate of discounting, the amount by which I increasingly discount things over time, the rate of sort of additional discounting is constant over time. And this comes back to Pedderman. One of you asked this question about why would that be the same every period. There's no particular reason to think it would be the same every period, unless you like the math. But that is the essential assumption that this model makes, and it has big implications, as I'll show you. Okay, so here are two big implications, and they're closely linked to one another. In some sense, they're really the same implication, as I hope you'll see. The first one is that the discount, what I'm calling time invariance of discounting, which basically means that if I wanted to compute what your delta is based on observations of the trade-offs that you're willing to make between current outcomes and future outcomes, the delta that I come up with should not depend upon how far in the future the delayed outcomes are. Okay? So if I'm experimentally trying to test or observationally trying to test delta, it won't matter whether I give you an experiment where I say, I'll offer you $100 today. How much would I have to offer you 2 weeks from now to make you indifferent between $100 now? It shouldn't matter whether I ask you that question or make it a year out. Right? The answer is going to be different, but when I then compute delta from your answers, I should get the same answer under this model. So let me show you that. Again, to just do this in super simple terms, let's again assume quasi-linear preferences so that the utility you get from money is linear. You just get 1 euro per dollar. Oh, this thing? I'm just trying to convince you that. So that thing there is f of x equals e to the x. It's that. Okay. Yeah. So you flip it over and you get that. Sorry. Thank you. Somebody should do a study of this IQ deficit problem. Yeah, I had drawn kind of like a weird hybrid of exponential and logarithmic. But this goes to show you can get a job as an economist without knowing very much math. Okay, so if I assume linear instantaneous utility function, if I'm indifferent between $250 now and some number of dollars xt at some future time period t, then I can compute, if you are indifferent, then I can compute your monthly delta. I'm sort of assuming that t is measured in months here, using discounted utility theory. Okay, so that indifference between 250 now and xt at some time in the future is represented, if I'm assuming discounted utility and linear instantaneous utility, it means that 250 in your mind is equal to delta to the t times xt, right? Because you're just getting 250 joules out of this, xt joules out of that, and then you're going to discount this future xt by some amount that's delta raised to the power of t, depending upon how many months out it is. And that means that delta to the t is going to be equal to 250 over xt, and that means that delta is going to be equal to 250 over xt to the 1 over t. Oh, whoops, 1 over t, or the t